Hello everyone! In this video, we'll be going over graphs of a function, its derivative, and its integral for Calculus Review for Physics 1510. Let's start with the graph of a function that we know. But first, we need to label our axes. Now, on a problem, the graph will always be notated if it's either the function, its derivative, or its integral. We'll be using the function y equals x, so this graph should be notated like y. The function y equals x is positively linear, so our graph should go up and to the right. Now, let's draw the function's derivative. The function's derivative, by using the power rule, is y prime equals 1. For the graph y equals 1, for every x value, the y value is always going to be 1. So we should have a horizontal line. Let's look at the integral. The integral of this function, by using the inverse power rule, is the integral of y dx, or x squared over 2. And because we're using an indefinite integral, we weren't given any bounds, we need to add a plus c. The graph of x squared over 2 normally looks something like this in the first quadrant. However, because of our plus c, it could also look like this, or like this. The starting y value, or height, will always be dependent on that plus c. And that's about it for graphs of a function that we know. Now, let's look at a graph of an unknown function and its derivative and integral. Let's graph something like this. We'll label the graph. And now we want to graph the function's derivative. We label our graph x and y. And we can either write y prime or dy over dx. If we use our definition of derivatives, we know that a derivative is really just the slope of the function. We make little tangent lines, or slope. We take the values of those slopes and we plot them on this graph. Our first slope is 0, so we plot our point at y equals 0, and then equally spaced out, our next points should be increasingly negative, but at a constant rate. We connect these together, and we'll see that our graph should be somewhere about linear. Finally, we want to look at the function's integral. Again, we label our graph, and then we use the definition of an integral. An integral is really just the area under a curve. An area is length times width of a rectangle. So we draw equally spaced rectangles, almost, and compare their areas. The first point should just be the area of the first rectangle. Now the next point is the value of the first point plus the area of the rectangle. This rectangle is a little bit smaller than the first one, so our next point should be a little less than twice the height of the first. Our third rectangle is a little bit smaller than that. Our fourth is even smaller. And our fifth is the smallest. We connect these points, and we should get a graph of the cubic order. However, because we weren't given any bounds again, we don't know if our graph will really start here at the origin or somewhere higher. Wherever it starts is the value of our plus c. And that's about it for these graphs. Thank you for watching.